Hey class, this is Bob, and we're gonna tackle what's called a shortest route problem in this video. So the shortest route problem, as the name implies, is a way to find an optimal path where the optimal means shortest. So what I've done here is I've drawn a diagram that might illustrate a situation we face, and let me just describe it. The arcs on this diagram represent potential paths we could take from getting from node 1 to node 6. And then the numbers along each arc represent the distance that's required to travel if you take that particular arc or path. We identify each arc using, again, xij as a binary decision variable, meaning it's going to be a 1 or a 0. If it's a 1, that indicates that we're going to take that path. If it's a 0, that indicates that we are not going to take that path. So in this scenario, we've got decision variables for every single arc. And some of the arcs have two decision variables because there's actually two directions that path could take. So for example, if you look at the nodes 3 and 4, you'll notice there's an arrow pointing both directions. So there's actually an x34, which corresponds to taking the path from 3 to 4. And there's also a decision variable called x43, which corresponds to whether or not we take the path from 4 to 3. So this is one particular scenario we might face. And what we're going to do is, it's pretty straightforward. We're going to want to minimize the total distance traveled, which will look like this. Minimize 4 times x12. Let's stop there and make sense of that. x12 corresponds to this path right here, going from node 1 to node 2. And it's a binary decision variable, as I said earlier. So that means that x12 is either going to equal 0, implying we're not taking that path, or 1, implying we are. So if this is a 0, 4 times 0 is 0, it won't affect the objective function. If it's a 1 and we do in fact take the path, it will be included. 4 times 1, it'll be included in the distance traveled that we compute. Okay, so we're going to complete this for all arches. So plus 4 times x13 plus 8 times x14 plus, and we'll keep going, you'd have 3 times x23 plus 3 times x32, because you could in fact go from 2 to 3, or you could go from 3 to 2. So that would look like this, plus 2x23. Actually, that should be, let's see, that should read 3 times x23 plus 3x32. This equation will keep going until we've included every possible arc, and it'll wrap up with, let's say, plus 4x46. Okay, so in this example, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like 12 decision variables. There's not that many arcs, but some of the arcs have are moving in both directions. Now, the shortest route says, hey, we want to minimize the distance we travel. Now what we have to do is impose through constraints, we have to impose this goal of leaving origin 1 and arriving at destination node 6. So if you think about it, if I want to go anywhere, I've got a couple of goals in mind. Number 1, I've got to leave. Number 2, I've got to arrive. And that just sounds silly, but there's a reason I'm saying that. Let's impose the constraint, or let's write the constraint that imposes this requirement that we leave. If we were to leave, that means that we take some route from node 1. So if we say x12 plus x13 plus x14, and we require that to be greater than or equal to, let's see, 1. Okay, that's supposed to be a 1. What have we done? Study that constraint. You may want to pause the video, but think about that. what does the left-hand side of that constraint represent? And what does it mean if it's greater than or equal to 1? Well, if it's not greater than 1, that means it's 0. And what that means is nobody left. X1, 2, nobody took path 1, 2. Nobody took path 1, 3. Nobody took path 1, 4. So this constraint ensures that at least one of the 3 paths available from node 1 are taken. So this is what you might call the somebody has to leave constraint. And similar to this constraint, you're going to have what you might call a somebody has to arrive constraint. And you might be able to write that. If you think you can write that, pause the video and write it. If you don't think so, here it comes. You're going to look at how do you arrive? X56 plus X46 must be greater than or equal to 1, meaning one of those 2 paths has to be taken. Somebody has to leave, that's this constraint, and somebody has to arrive. If that X56 plus X46 equals 0, that constraint is violated, and that would imply that nobody took those last paths and nobody could have arrived at node 6. So this ensures somebody arrives. The rest of the constraints require that if you leave a node, you had to have first arrived. I'm going to say that again. The rest of these constraints are going to state that if we leave a node, we must have first arrived. So let's look at node 2. And essentially every node will have a constraint. I'm going to say that again, make a mental note. On the shortest route problem, every node will have a constraint. We've already written a constraint for node 1. We've already written a constraint for node 6. And now let's look at those internal nodes. Let's look at node 2. If you leave, whatever leaves must equal whatever came in. So we can write it this way. Let's look at every arrow going into node 2, and we see that X1, 2, and we have also X3, 2. Okay? So that represents what's going into node 2, and that has to equal everything leaving node 2. So how do you leave node 2? You either go to node 3 or you go to node 5. So we'll say X2, 3 plus X2, 5. Okay? So what have I done here? I've ensured that if you leave the node, whatever leaves the node must equal whatever came into the node. So we ensure that we aren't just leaving, if you will, appearing out of nowhere at a particular node. We have to have first arrived there. So this is a very basic constraint, similar to a transshipment node constraint that basically says what goes in must equal what comes out. Okay, so you're going to have this constraint, this type of constraint for nodes 2, 3, 4, and 5, and that's it. So to review, you've got a minimization objective function that minimizes the distance traveled, where your objective function represents the total distance traveled. Now most of these decision variables are going to equal 0, and they won't be included in the distance traveled because you won't take those routes. And this will force the software package to, in Excel, for example, to find the way to get there in the shortest route. And these constraints impose reality upon the problem. They say that, hey, somebody's got to leave, somebody's got to arrive, and you can't just arrive out of nowhere. If you leave from a node, you have to have come from somewhere. And that's what those constraints ensure. Okay, so that's the gist of a shortest route problem. Again, I did not draw all of the constraints. I only wrote one constraint for node 2. So I have not written constraints for nodes 3, 4, or 5. But essentially, they are what goes in, the arrows pointing in must equal the arrows coming out. So for node 3, for example, let me just verbally say what that one would be. What goes in? X23 plus X13 plus X43 must equal what goes out? X32 plus X34. 4. Okay? Do something very similar with node 5. x25 plus x45 equals x54 plus x53. I'm sorry, 56. Okay? It's just that simple. And that's the shortest route problem, and we'll wrap it up right there.